So it is my pleasure to introduce Zubin Jacob, who is now going to be our speaker today. I have known him when he was in Canada. I don't know exactly at which institution, but currently he is Associate Professor of Electrical and Computer Engineering, and he has a courtesy appointment at Department of Physics at Purdue University. He got his initial education in India at ITT Bombay, where he got a Master of Science in Electrical Engineering. And then he went to Princeton University, where he got his PhD. And since 2010, he was at Purdue University. He has a very active research program. He's a visitor of DARPA's Directors Fellowships, National Science Foundation Career Award, DARPA Young Faculty Award, and Purdue EC Outstanding Graduate Student Mentor Award. And he will tell us about I don't know what his title is, but he'll tell us how to make photonic and Dirac and maybe I should find the title.
Yeah, I made my title a lot simpler.
Maxwellian phases of matter too.
Yes. Yeah, I made sure that the title is very simple and kind of straightforward. So first, let me thank PTEC for inviting me. It's a pleasure to be here. And as PTEC mentioned, we've known each other for many years now. We've been off and on in touch about many things, including the wonderful background that you see behind PTEC of this very fancy structure of light. And we've been working on that as well. And I'll try to talk to you a little bit more about that and hopefully find ways for our groups to collaborate. So that's the kind of big picture here. In a nutshell, we want to talk about the spin of the photon and many of its manifestations. And much of this work is being done in my group since I moved to Purdue. This is our website for those of you who are interested. So quick picture about the group. This is my group. A lot of the work that I'm going to present today is done by a subset of students. There's Todd. Also, there are a couple of new, there's a new postdoctoral scholar, Dr. Satvik Bharadwaj, who's also working on the spin aspects, and there's also Wenbo. So quite a bit of the work will be from Todd and Wenbo, but I'll also talk a little bit about the work from Farid and Farhad today. So let me try to explain where we started and where we are going with all of this research. So I guess I just want to make sure, Jenny, can you hear me well? Like everything is
Yeah, you're very
okay? All right, great, thank you. All right, so here it is. That's the outline of my talk. I do want to talk about topological phases of matter. This is a very important area of research in condensed matter physics. I want to give you some of the results from my group. But I want to give you the bigger picture of where we started and where we are headed with all this research. So I'll tell you a little bit about the classical and semi-classical results related to the spin of the photon, because this ends up being the very nice rigorous starting point to develop more advanced theories. I will tell you a little bit about the topological theory that we have been developing, where light is coupled to matter, and we end up seeing some very interesting phases of matter. And then finally, I'll just have one or two slides about how we are looking at the quantum nature of light and the quantum nature of spin. And this is very recent work. And I'll just have a slide or two about what we are doing. And we are also planning quite a bit of experiments in these areas. However, today's talk is going to be mainly theoretical work. So all of this stuff that you're going to see is going to be mainly theoretical work. So let's get started and try to ask the question, what is spin photonics? It turns out that there is quite a lot of groups working uncoupling light and matter, but more specifically the spin degree of matter. And there's a very beautiful recent work from PTEC's group as well. And this is some of the work around 2015 and a little earlier from Arnaud Rochenbottel's group and Barak Dayan's group, where they were looking at cold atoms trapped near a nanofiber. So it's a very, very subtle and difficult technique of trapping these cold atoms near nanostructures, and they coupled it near a nanofiber. And then what they noticed is that these cold atoms preferentially emit spontaneous emission and have very unique directional scattering properties related to the handedness of the light and the handedness of the spin inside here, or handedness of the kind of cold atom transition. Another very different system, completely different from this, has been studied by the Kuiper's group in Netherlands, where they have 2D excitons, 2D material excitons, coupled to a silver nanowire. And when you look at these 2D excitons, which have spin orbit coupling coming from the heavy element in here, you can see that the light which is emitted once again has a highly directional nature of going in only one direction. Another experimental system is from Peter Lodal's group, where there is a quantum dot coupled to a photonic crystal or a cavity system. And then once again, it was noticed that if you have a quantum dot, it again has spontaneous emission as well as scattering properties, which are very directional based on the type of transitions that you probe within the quantum dot, a sigma plus or sigma minus transition. And another very nice experiment is from Nakamura's group in Japan, where they have magnons in a Yig sphere. Yig stands for yttrium iron garnet, and it's a magnetic material at low frequencies. And they were able to show that even the magnonic modes, when they couple to the nanofiber, they have the same sort of handedness that the light has. And this is a whole broad set of experiments in many different systems that all show the unique unifying behavior, that is routing and directionality of photons depending on polarization or the handedness. So when we looked at this kind of problem in detail, more specifically the Rochenbottel paper, one thing we realized is that this is a phenomenon which is very unique to the nanoscale. And there were questions in the field during that period of 2014, 2015. Is it a topological phenomenon, this routing of light? Is it a quantum phenomenon? Or is it related to the orbital angular momentum in some way? Is it related to chirality of light? Is it related to helicity? So there were all these terms in various papers as well as conferences that were trying to kind of address this phenomenon. And one of the things that we pointed out, this was kind of the early work, and we pointed out that we can understand this phenomenon completely classically, or rather semi-classically, because you have a quantum emitter coupled to a nanophotonic structure. So, and we coined the term spin momentum locking, that there is actually an intrinsic spin to the evanescent wave, which is locked to the momentum. And this is actually universal. It is not specific to one realization. It occurs in every possible system you can think about, from the silver nanowire to a silver interface to an evanescent fields and an air dielectric interface to the optical fiber. You will see that there is a tumbling behavior of the electric field vectors in each of these evanescent fields, which are always present in nanophotonics. However, the most unique aspect is that there is a locked triplet between this spin, which is intrinsic to the evanescent wave, the momentum, which is the direction of propagation, and the decay vector. And we were able to show that this is actually universal behavior, that there is going to be this locked electromagnetic triplet between the spin, the decay, and the momentum. Now, this becomes much more clearer if I show you a movie. Let's actually just look at the case of the optical a fiber. And we are all familiar with the concept of polarization of light. It is a global handedness. However, here we are talking about something slightly different. We are talking about a density of polarization. We're talking about local polarization, which varies from point to point. Let's see if this movie plays. Oops. So it seems that this movie does not play here. I should have checked this. Let me see if I can kind of skip out of a full screen mode. Yes, can you see the movie now?
Yeah, I can.
All right, perfect. So this movie is the best way of understanding kind of what's going on. You will see that the local electric field vectors at every point are rotating in the optical fiber. This is a lateral cross section. The mode is moving in the z direction, and you will see that there is clearly a handedness at every point. This is what we really mean by a local polarization. And for differing sizes of the fibers, you will see that there is actually also going to be a transverse kind of rotation of this electric field, which is called a transverse spin. Let's take a quick look at this figure as well. You will see here that once again, this is in the z direction as a propagation. This is kind of an x z cross section here. And you will see that the electric fields are kind of rotating in this form. And this is the local rotation of the electric field, which can in principle vary from point to point. And it can even, the planes can also be different for the rotation. That's what we mean by spin density, which is very different from the case of a plane wave, where the concept of spin is pretty much the concept of helicity, where the spin is along the direction of momentum. It need not be the case for ultra confined structures. And what is interesting is that this handedness that you're seeing, I mean, it rotates either clockwise or counterclockwise. You can see for this one, I mean, this is rotating clockwise. This handedness is determined by the direction of propagation. If I reverse the direction of propagation, you would reverse this handedness. So these are, for some of you who are interested, these are papers where you can go and read more about it. One of the things I wanted to mention is that these states which are propagating in the forward and backward direction have the same energy. So you just reverse the direction, you reverse the handedness, but there is no concept of non-reciprocity or chirality, which requires a lifting of the energy degeneracy. These modes are energy degenerate, and this is why we call it a spin momentum locking as the key aspect. This handedness is locked to the direction of propagation. There's one more movie that I want to show you, because this is also something that will give you a clear picture of what's happening. You can immediately ask the question, how do we excite such a mode? So here, what you're seeing is a spherical resonator. This is not an optical fiber anymore. This is a spherical resonator. And we bring in a atom or a quantum dot which has a Zeeman transition. So you bias it with a magnetic field such that you select either a sigma plus or sigma minus transition. And that's what we have, this small green, this one plays. So if you see the small green arrow which is rotating, it really stands for a cold atom with a Zeeman transition. And then you solve the problem semi-classically, and you will see that there is a clear orbital angular momentum which is coupled to the local spin density of this field, and that spin density is coupled to the Zeeman transition. So one thing that is very important to remember is that we are talking about a clear difference between a local spin density right here, which is a microscopic property, and the orbital angular momentum, which is really a wavelength scale concept. So there's a clear difference between the spin density and OAM density. And the other important thing to remember is that spin is actually an intrinsic degree of freedom for any particle. Both fermions and bosons, spin is what distinguishes them, and it's an intrinsic degree of freedom. And the spin density is a local polarization. And what we've also been able to show that this is universal behavior. Even if you were to look at Dirac waves as solutions of Dirac equations, many of these ideas do translate over to the relativistic wave equation that governs fermions. I will not go through that in detail, but some of who you are interested, please go through this paper. So now with this sort of a semi-classical background, is there a question?
Question.
Yes.
In the previous slide, when you said that you reverse the direction, are you talking about, I mean, helicity is a pseudo-scalar.
Yes.
Helicity is a pseudo-scalar. So in principle, if you reverse the direction, there should be a reversal of helicity as well. Was that what you were talking about in the?
No, actually slightly different. So maybe this figure is what kind of explains it a bit better. So you will see that this evanescent wave, which is kind of leaking out of this material, strictly speaking, it's not a helicity, because the helicity is the projection of the spin along the direction of propagation. But here you will see that the spin is perpendicular to the direction of propagation. So if you look at this figure right here, this tumbling behavior of the electric field is actually in a plane perpendicular to the momentum. So this is not, strictly speaking, it's not the helicity of the photon.
But then there is a component of the orbital angular momentum as well that is projecting on the perpendicular direction. I mean, if you project on the parallel direction to momentum, then the orbital part cancels out, right? It doesn't have any component there. But if you're looking at the perpendicular, there has to be a component from the OEM, right? Orbital angular momentum. Right?
Okay, so there is going to be a component, but those are actually contributions which are maybe at the wavelength scale. But here we are talking about at a local microscopic ultra sub-wavelength mode or ultra sub-wavelength location of the electromagnetic field. So there, the concept is becomes completely dominated by the spin angular momentum as opposed to the orbital angular momentum. So this is so another way of understanding this is the following. Let's take the case of just total internal reflection, right? So you have a plane wave coming in. Now, if it's a plane wave and we have a linearly polarized plane wave coming in, we know that this can be mapped to if a completely kind of linearly polarized plane wave, we can map it to a mode which has no spin angular momentum, because it's both RCP and LCP equal superposition. And you can also show that the OAM is zero. There is no phase singularities for there to be any orbital angular momentum of the field. So in that case, when total internal reflection happens, this tumbling behavior is really coming from an intrinsic spin angular momentum as opposed to an orbital angular momentum. And another way of seeing this is, if you look at this figure right here, which is in 3D confined model, is that you have just a point source which has a sigma plus transition. So the selection rules itself give you, say, one photon. If there was just one atom, there would be just one photon. And the selection rules itself gives you that there is a orbital angular momentum change that corresponds to, say, sigma plus transition. And this OAM change is right here, but the spin density is the local one at the location of the atom. So that's how we distinguish between the OAM and the spin. I'll come back to this point in the talk again. This is a very good question. And so now what I want to talk about is actually the kind of the bulk of the talk here is much of the previous things that I mentioned can be understood semi-classically, and it does not have a topological origin. So this led us to ask the question, I mean, how does spin and topology connect with each other? How does the topological nature of edge waves and topological nature of spin momentum locking manifest itself for light? And this was an interesting question, and we have some rather subtle answers to this problem. And so let's look at the kind of quick introduction to a slightly different field of research. I've been talking more about cold atoms and nanophotonics, but here let's actually look at the topological connection to the spin of light. But to appreciate that better, we have to look at what is known as a Chern insulator, or what is known as a quantum anomalous Hall effect. We've been talking about that spin of the evanescent wave going in a certain direction. Now, it turns out there are unique materials, and these were proposed essentially in the context of the quantum Hall effect, that there are materials in which you can have these edge waves, and the edge waves are such that they only go in one direction. You just do not have a wave in the other direction on the edge at all. And furthermore, they contribute to a quantized conductance, and this is an edge conductance, and the bulk conductance is 0. So there is no electrical conductance in the bulk, and all the conductivity is coming from the edge. And this is sometimes called the Chern insulator and the anomalous Hall effect, because you can get these effects even when the net kind of magnetic field is 0. And this is a generalization of the integer quantum Hall effect. So we wanted to study first, what are the experimental realizations of this, and then how do we think about this in the context of photons? So let me give you a quick understanding of how it works in the condensed matter context. Even though the basic theory was well established in the 1980s through the Haldane model, it took actually more than 3 decades before there were basic experiments in the 2010s. And now you see this large explosion of activity in trying to understand different materials, different edge conductances. And this is one of the first realizations of the quantum anomalous Hall effect. Here they had a topological insulator film, which was doped with some magnetic impurities so that you have a sort of magnetization. And it was shown that you will have only edge currents in such a solid state material. So these were chromium dopants in bismuth telluride. So this is one of the early examples, and now we have actually, I would say that more than 50 or 100 examples of such Chern insulating phases. Now, in the context of photons, this work has inspired some very interesting achievements. In the context of photons, Raghu and Haldane had early theory that we can build photonic crystals which will have the same type of edge effects. And there's also very nice work, the experimental work, which was done by Soliacic, following up on Raghu Haldane, and some very nice work in the optics as well from Moti Sagev and Rexman, all related to the concept of topological photonic crystals. So let's see what's happening. So to mimic the edge state of the condensed matter system, what has been done in the field of photonics is that you have these rods which are carefully engineered, and they are fixed in position. And then you come in with a microwave antenna. Right here is the antenna, and you excite the wave, and you will see that the wave does not go into the bulk. There's a bulk band gap, and the wave only propagates on the edge. And even if you have a scatterer over here, that in principle should actually scatter light backwards, because there's only one way propagation possible, the wave just moves around the edge and goes ahead. And this was kind of demonstrated experimentally. And here is actually the structure right here. And this is made of ferrite rods. So we were quite intrigued by the connection between condensed matter and topological photonics, and led us to ask a very different question. Let us actually zoom into each of these rods, right? And these are ferrite rods. Again, it's a sort of garnet made rods in here. Now, these size scales are 4 centimeters. If you zoom into this ferrite rods and ask how does light interact with the ferrite rod microscopically, we will see that it is in a trivial phase of matter when it comes to light, because microscopically speaking, the ferrite rod is a conventional material. So we started looking at the question, inspired from our work from spin, is can we think about phases of matter where the spin plays a very fundamental role? And then you can actually look at the atomic scale behavior of an atomic crystal as opposed to the photonic crystal metamaterial and resonator limit. Can we bridge this knowledge gap? And so here, these edge states are well known and discovered. You have these scatterers which are arranged in a very clever way, and you have an edge state that goes in one direction. Can we have an atomic system in which you have an electromagnetic edge state going in one direction? So this is what we kind of like to call these Maxwellian phases of matter. And the answer that we found after quite a few years of work is that yes, this can exist. And for some of the condensed matter experts in the audience, just wanted to mention that here we are talking about real U1 gauge fields coupled to charges. So you're talking about kind of a interacting field theory. Here you're talking about a free field theory, which does not lead to large induced currents inside the material at all. And another way of thinking about is, again, for the experts, is that this is related to the geometry of the electromagnetic fields inside condensed matter. So it's very different from the geometry of the electron wave function in condensed matter, which is very well known. So, so the way we kind of looked at this problem, and I think that we're roughly at halfway mark, and I think this is kind of where I expected to be. This gets into a little bit of the details of kind of the materials physics and condensed matter physics, where I want to contrast the way we study band structure of atoms inside a solid with the concept of polarization cloud and magnetization cloud that the photons see when they are interacting with an solid like this. So one of the things that we found as a necessary ingredient to start seeing photon spin effects in condensed matter as well as topological effects is a form of non-local conductivity. That is to say, a conductivity which varies with has temporal dispersion and spatial dispersion. So all our theory is really connected to a theory of conductivity in much more detail. So let's see what that detail is. So to look at the detail, and considering this is a very broad audience, I am going to take an example of gold because this is something that we all are familiar with. And I'll go through that example, and then we'll come to the interesting aspects of conductivity that we have found. So when you say you are going to perform some measurements on gold and you're going to characterize the material, I mean, one of the first things you'll do is look at the resistivity. Now you will apply a voltage in response to a field. There's going to be a current, and then you will characterize the DC resistance of gold. However, one has to remember that gold has not just the DC conductivity at zero frequencies. When you talk about this material with respect to the photon, you're going to have a frequency axis and momentum axis, and you're going to have a bunch of different types of waves at various frequencies and momenta that characterize gold. So there's a terahertz, you'll have a very weakly interacting, weakly bound surface wave. Then you have the interband transitions of gold in the visible. This is what gives gold its color. That's where the yellow color comes from. It comes from the interband transition. And you have this surface wave on gold, and these are at above the plasma frequency, you have the bulk waves. So to really characterize gold, it's not enough to just do the DC conductivity measurements. You do have to look at all the measurements all together. So the important point that we are trying to make here is that when we look at conductivity of a material, we have to look at the DC conductivity, need to look at the visible, terahertz, and pretty much very high frequencies as well. And all of them are connected to a Kramers-Kronig or causal response function. This is why we write down a concept of conductivity in this form. Sometimes this is also called an optical conductivity because it varies as a function of frequency. It's also known, if you perform a more rigorous analysis using kind of band structure or Fermi liquid theory, you can see that the conductivity is actually a function of frequency, and there are also corrections to the conductivity coming from the momentum. So these are quadratic corrections, and the correct way of writing down conductivity is a function of frequency of light and a function of momentum of light, which is borrowed by the electrons as you shine light on it. So this is the concept of conventional classical conductivity that we all understand. There's nothing topological about this conductivity at all. If you take gold, this conductivity is not topological. However, there's been one very interesting, case that was discovered in the 1980s that completely took the research field by storm at that point, because what was shown is that if you consider a 3-5 material, and more specifically a 2-dimensional electron gas, in 2 dimensions, if you perform the same type of DC experiment with a voltage applied, so you have a field and you also apply a magnetic field, then the longitudinal conductivity in this direction is actually 0, and you only have a transverse conductivity. in this direction. And this is a dissipation-less case with no heat. And classically, you will expect things like resistivity to just vary linearly with the magnetic field. But instead, what was noticed was a quantum phenomenon that you have these plateaus in the resistivity such that the transverse conductivity, which is also known as the Hall conductivity, is quantized. And this was very, very surprising at the time of discovery, because you have only fundamental constants entering your conductivity, Hall conductivity. It's not really just some classical function which varies with kind of samples and the disorder in the sample or the applied magnetic field. These are fundamental constants, and n is quantized to an integer with very, very high accuracy. So this was a puzzling discovery, and this led to the Nobel Prize for von Klitzing, and there's been lots of theory that led to a deeper understanding that this is a topological quantity, and this quantization right here, n, has connections to the geometry of the wave function. Here, the point that we want to make is from a completely theory point of view and from the photon point of view, one has to look at this Hall conductivity as a zero frequency, zero momentum quantization. That is when you get ne squared by h. This is all at low frequency and low momentum. So the topological invariants which we are conventionally used to defining are not connected to the photon. They have zero frequency and zero momentum. And that's where we kind of made this note and started looking at this in more detail. And I'll tell you kind of what we have found. I'll tell you the answers and so forth. But I do want to talk about one experiment from 2010, probably like maybe 30 years, 25, 30 years after the original experiment, where there was a very convincing terahertz experiment on optical or dynamical Hall conductivity, where they shined a terahertz pulse through the two-dimensional electron gas. There was an applied magnetic field. And what they showed is that at low temperatures, the terahertz pulse has a rotation. This is known as Faraday rotation. In plasma physics, they call it gyrotropy. If you are from photonics or spintronics, you sometimes call it magneto-optic media. This is a form of Faraday and Kerr rotation. And this plane of polarization is rotated as it passes through the two-dimensional electron gas. And when you try to analyze this Hall conductivity at optical frequencies, they noticed plateaus. They noticed the same quantization that is present at DC frequencies. So this was one of the first convincing experiments that this behavior exists even at terahertz frequencies. So let's put all our knowledge together. You can think of all the example that I gave you as that of a 2D electron gas or a 2D quantum fluid. We have one axis frequency, another axis momentum. And the early 1980s work is all connected to the zero frequency, zero momentum Hall conductivity. The 2010 paper that I just showed you is a high frequency, but it is still low momentum because you're coming in with light in free space. So that's the optical Hall conductivity from 2010. And they measured some interesting properties here. But what we want to look at is actually out here. This is a Hall conductivity at low frequencies, but very large momentum, really sub-wavelength behavior of the Hall conductivity. That's how one has to think about it. And the main result that I want to talk about today in a nutshell is that when you look at Hall conductivity in a dynamical sense at higher frequencies and higher momentum, you end up seeing new Maxwellian phases of matter when you probe this regime. So this is a slide for the theorists. The way you approach the problem is by you looking at mass in the 2D Dirac equation. So in the 2D Dirac equation, mass has a very, very kind of clear understanding that it opens up a low energy band gap. It has a curvature and it breaks the symmetry of left and right. In a way, is a time reversal symmetry. And if you write down a Maxwell Hamiltonian, instead of a Dirac Hamiltonian for matter, you write down a Maxwell Hamiltonian for matter. This Maxwell Hamiltonian is not directly aware of the microscopic wave functions, but the Maxwell Hamiltonian is aware of the Hall conductivity at sub-wavelength scales. And you can show that the way the mass enters the Dirac Hamiltonian is the same way the Hall conductivity enters the Maxwell-Hamiltonian. So Hall conductivity plays a role of a dynamical photon mass or a Chern-Simons mass in the Maxwell-Hamiltonian. I'll skip this slide, and for the experts, I'm happy to discuss a Maxwell-Chern-Simons theory that we recently developed to put all of these kind of intuitive understanding on a rigorous platform. So this is kind of the answer right here that we had found. I mean, it was just a model at the point we found it. It was a theory that if you consider a Hall conductivity very, very carefully, which depends on frequency and momentum, you can see some new types of electromagnetic edge states going only in one direction. You can see that there's no symmetry. The branch only goes in one direction, and we might be able to see this and also see ideas of spin momentum locking and spin quantization in photonics for the first time. So here was the roadblock. I mean, this was some of the early papers. In fact, I remember sending them to PTech as well. And PTech mentioned, I mean, what are the kind of the experimental consequences? And the truth of the matter was, the early times when we were 2018, 2019, we actually did not know the experimental consequences. But lots has changed since then. Recently, we realized there is a very, very interesting connection between what we found and the idea of Hall viscosity, which was only shown for the first time in 2019. So in April 2019, there was a breakthrough paper from Andre Geim's group and Marco Polini doing theory, where they showed that if you take graphene's electron fluid, where graphene has pristine samples where the charge transport is dominated by electron-electron interactions, you can start seeing a hydrodynamic behavior of the electrons in graphene. And there they showed that you can probe this K-dependent nature of the Hall conductivity, which is also known as Hall viscosity, because you're dealing with an electron fluid. So this kind of got us very excited, because we realized that this same system should be the exact playing ground for the photonics in the problem as well, or the electromagnetic waves in the problem as well, which was not considered in this study, was mainly all DC transport. So what is Hall viscosity? Let's try to understand that from an intuitive point of view. And Hall viscosity is essentially the deep subwavelength behavior of Hall conductivity. That's how one should understand it. And it has a very important consequence for light as well. Here, what you're seeing is a shear viscosity that we are familiar with. When you say that water flows more freely than honey, what you're really saying is that honey is a highly viscous liquid. Water has lower viscosity. Water flows more easily. And that's what you mean when you say that, I mean, you have a thick liquid of honey. And here what you're seeing is that if you were to kind of rotate this fluid, then there is going to be an opposing force within the fluid, which is tangential to your direction of rotation. So you rotate the fluid, there's going to be a little bit of friction and resistance to a fluid. This is what is known as shear viscosity, very well known in fluid dynamics as well as plasma physics. However, Hall viscosity is something fundamentally new. It is a completely dissipation-less response of a fluid. When you try to rotate it, it actually couples to a linear momentum in the orthogonal direction. And you can clearly see it's dissipation less because it's orthogonal. So you're really coupling a linear momentum to an angular momentum. In other words, you try to shear a liquid and there is small angular momentum set up, a small kind of cyclotron motion set up in the liquid because of the external magnetic field and the viscous nature of the fluid. And here we are forming an analogy between a fluid and a strongly interacting electron gas. So what we did, we got excited by this and we mapped our earlier model, which was the viscous Maxwell-Chern-Simons theory, to a model which has Navier-Stokes equations, because this really is a kind of gold standard of looking at strongly interacting electron fluids. And we added a Hall viscosity to it. Then we added Maxwellian electrodynamics to it. We had new boundary conditions from action minimization, and we used the parameters from the Graphene 2019 paper. And this is essentially the geometry that we have considered. It consists of graphene on a substrate, but this is a graphene which has Hall viscosity. This is an applied magnetic field. And then we kind of solve this system of equations for this geometry. The key point is that we are looking at low frequency waves, and also the size of this structure is way, way smaller than the size of wavelength. So going back to the 4 centimeter scale ferrite rods, I mean, we are talking about micron scale or smaller than micron scale for the whole sample over here.
Daniel, did you have a question?
Yes.
Question. Yeah, so I'd like to understand this dissipation-less viscosity, because if I put this within the perspective of a Navier-Stokes equation,
yes,
if I make a perturbation, that perturbation is going to decay in time as a hydrodynamic mode with a coefficient that depends on the viscosity. So there is dissipation
yes,
of a perturbation. So when you're talking about viscosity and dissipation-less viscosity, what is it that you're actually talking about within the context of a fluid description?
yes. So you can think about it as energy stored in the fluid, energy stored inside the fluid. The perturbation only leads to certain orbits inside the fluid, which leads to stored energy. It's not energy which is dissipated. That's an intuitive way of thinking about the answer. Yeah. So the conventional viscosity will lead to a decay, but you can also store energy in the perturbation, store energy in the fluid due to the perturbation. And that's the extra term in the Navier-Stokes equation. A conventional fluid model will not show this effect. Every perturbation will only decay.
The other question related to that is typically when you have a shear viscosity, you also have a bulk viscosity, and they are somehow related, at least with sport formulation, they are related. Is there such a thing as a bulk viscosity in this particular case as well?
Actually, in this case, there is no bulk viscosity at all because I'll have to think about this. In this case, the kind of intuitive answer I can give is that we are looking at a Hall conductivity, which is dissipation less. And this is a sort of correction to the Hall conductivity. So the equivalent bulk response is going to be the Hall conductivity. And that is itself dissipation less. So that's where the connection would be. Now, so what I want to do is kind of show you the simulation results of our kind of detailed model here. These are all the parameters directly from the experimental paper from 2019. We do have a kind of shear viscosity included because there'll be a small damping no matter how pristine the sample is. And you see something very interesting. So this is the geometry, and we're looking at a top view. We have 3 kind of point contacts or STM tips, if you want to think about it like that, which is exciting this charged viscous Hall fluid. And you see that there's edge states which are moving in one direction, which you can think about it as a kind of topological viscous Hall plasmon, where you have a electron fluid which is coupled to the electromagnetic field, and there are edge states which are very different from conventional edge magnetoplasmons. And they are only going in one direction. And you can see that even if there is small kind of edges, there is no back reflection at all because there is no backward propagating edge wave at all in this system. So such an edge wave in graphene has not been demonstrated experimentally at these kind of frequencies. And we think that this is quite a viable experiment that can be performed. Of course, we need kind of similar pristine samples and probably a Tesla magnetic field. So now comes to the point, I think this is probably something that PTech kind of enjoys as an area of research. We pointed out a connection between the concept of a skyrmion in momentum space and the edge state that is present in this fluid. So let's see what we mean by that. So skyrmions correspond to a pattern of spins with a tumbling behavior say magnets, for example. But you can also have a tumbling behavior of the spins in momentum space. So if you look at not the edge waves, but you look at the bulk waves in graphene at these low frequencies with Hall viscosity included, we see that the spin vectors in momentum space, these are not spin vectors in real space, they will have a tumbling behavior. And close to the region of the tumbling behavior, the edge state will go and close the gap and it will touch the bulk state. And this is what is fundamentally different from a standard edge magnetoplasmon and this topological viscous Hall plasmon is this edge kind of touching the bulk. So we have some experimental signatures that we have provided as well using a kind of MOOC. There's a little less time remaining, so I just want to give you a summary for the experts in the audience. I mean, this took, of course, a long time for us to come to it, but once we have the answer, it seems very intuitive. That there's the Chern insulating phase in graphene, which is very well known, which is graphene with next nearest neighbors hopping. The Haldane model is characterized by a Chern number, which belongs to the Z class. So you just have kind of all integers for the Chern number that classifies this phase of matter. You have a quantum spin Hall insulator where there is graphene with spin orbit coupling. This is the Kane-Meillet model. And you have a Z2 invariant associated with this phase. The problem that we are looking at is the case of graphene with Hall viscosity. And here you have an optical N invariant, because in these two problems, you don't need to couple the light to the problem to see all the modes very carefully. Here it's an electromagnetic topological phase because you're dealing with electromagnetic waves and graphene and Hall viscosity. And we showed that there's a new invariant connected with this, and there's an optical N invariant. So this is a quick and basic summary of what we have found over many years and multiple papers in the most clear and succinct fashion. This type of graphene with Hall viscosity, which has these interesting properties. So now I just have maybe 5 minutes left, or maybe 2 minutes or 3 minutes I want to take about how we are taking all of this understanding and now going towards kind of the quantum nature of spin, not only in matter, but also in free space. And this required us to look at an actually old problem on the quantum spin operator of the photon. So much of the work on observing kind of the polarization and so forth is really tied to the classical limit of spin. And one of the things is that there's been a lot of work, and in fact, I mean, if you look at this paper, this is a nice paper, you can look at the photon angular momentum controversy, that there's actually a problem that there is no spin operator for the photon that has been defined till date. And that's really connected to the fact that the spin operator does not obey the commutation relationships as we had expected it. This was one of the problems that were pointed out, kind of long-standing gauge invariance problems. So this is has been a problem in the community for a long time. And the reason this is of interest to a lot of researchers is because all particles in nature can be classified as bosons or fermions. And spin is what defines the difference. For the fermion spin, we know the operator, but for the, which is the electron spin operator, but for the photon spin operator, we actually don't know this. So this April, we found something very interesting, which we think is really the quantum spin operator of the photon, using a relativistic formalism for electrodynamics, which is U1 gauge theory. And it's a very subtle form of a Fermi Lagrangian that is needed. And we now have a spin operator for the photon that allows us to look at all our theories in the quantum sense. And the reason we are very confident that this is correct is that these operators obey the same commutation relationships as the well-known Dirac spin operators. So these spin operators obey a commutation relationship that we all know. And the spin operator of the photon, as we have found, also shows the same commutation relationships. And that's why we feel that this is really the way to go towards the quantum nature. So this just brings me to the summary of my talk. Here, I started with talking about kind of the semi-classical picture of quantum emitters coupled to nanophotonics. and we spoke about the spin as manifested in various structures and the universal nature of spin momentum locking. Then I spoke about the topological consequences of spin. The topological nature of a viscous Hall fluid, when it couples to light, you start seeing edge states with spin quantization, edge states with topological robustness, edge states which are only going in one direction. It also has a spin 1 quantized skyrmion in momentum space. And we think this is a new phase of matter because it is classified by a new topological invariant. I predicted some of these experiments that can also be done. And then recently, we have found that the spin operator can really be written in a completely quantum way. And we think that we can now start looking at going from spin photonics, which is really semi-classical, to topological spin photonics, to really a spin quantum electrodynamics, where a lot of relativistic and interactions between light and matter can show these spin effects. And we are kind of excited about the prospects. And I'll be happy to kind of come back and tell you what we find on the quantum front as well. So this is my talk for today. Thank you for your attention. I'll be very happy to answer questions.
Thank you very much. That was really interesting. If anyone has questions, they can feel free to unmute and ask.
In two space, one time dimension, one can add to the quantum electrodynamics action another term which is called the Chern-Simons, that basically breaks parity and also time reversal invariance. So I wonder whether the effective theory that you're describing in two spatial dimensions can be condensed in terms of an extra term in your Hamiltonian or Lagrangian days. I mean, it's allowed in two space dimension, but not in three, right? But
right. Okay, so this is a really good question, Daniel. So, so that theory, I mean, there's a Chern-Simons term, and then of course we have you can add in the Maxwell part to it. So it's a Maxwell-Chern-Simons theory. However, we found that actually Maxwell-Chern-Simons theory directly does not reproduce our results. We have to make it viscous. There is an additional term on top of Maxwell-Chern-Simons theory that is needed to actually reproduce our results. And we just kind of got that paper out in PRB recently. And that's a really good observation that there is a Chern-Simons theory, certainly, but it is a viscous Chern-Simons theory. There's an additional kind of term required to observe these edge states going in one direction and this electromagnetic classification, or the skyrmion, for example.
Well, I don't know about the skyrmion, but so this viscosity is not a Hamiltonian term, right? Because you say that it doesn't conserve energy, right? So it cannot lead to a Hermitian Hamiltonian.
So let me put it this way. For example, even in the Chern-Simons term, like if you only had the Chern-Simons term, then it does not contribute to the energy. It will disappear in the Hamiltonian case. And that's exactly what's happening here as well. So there is a correction term to the Chern-Simons term that we have added to reproduce our results. Yes. Yeah, and that's a really good question.
I would like to ask, so in optics, we are limited by energy time uncertainty, and we're limited by wavelength. So we cannot image easily on sub-wavelength scale.
Yes.
And so with spin, do you have any physical limitations in terms of imaging spin or?
No, this is actually a really good question. I mean, I think that it would be really nice to kind of develop techniques where we start looking more at the sub-wavelength behavior of these electromagnetic fields that we study, for example, through PEAM. If there was a way to polarize the electrons with a certain handedness going in, or spin filter the electrons kind of coming out, for example, definitely go in with a circularly polarized pulse, and then maybe study the spin filtered electrons coming out, which might be something that you might already be able to do. I think that some of these features will start manifesting itself. I understand it's very, very difficult. And we are thinking about the possibilities. At this point, I think that the only proofs we had are kind of indirect. I think if we were able to really map this edge state very carefully, then this would be very interesting. And there is a technique that we just recently found. I think it's like impedance microscopy, like very, very small tip that goes over your sample and measures the impedance at each point microscopically at gigahertz frequencies, like up to 10 gigahertz. So it's a tough technique, but I think these effects would be within the scale that such impedance microscopy captures.
So since you're at this slide, what is the frequency here and the spatial scale?
Right, so I'll give you the rough numbers. The frequencies are between gigahertz and terahertz. So that's kind of roughly the frequency scale. And the size scale actually is much more really flexible. We can have macroscopic samples with 10 microns or 100 microns very easily. There is no problem at all. The theory will definitely work. I think if you go below 10 microns, then we have to think much harder whether this theory will work. But 50 to 100 microns, certainly this theory will work.
Okay.
Yeah.
Thanks.
Can I ask another question?
Yes, Daniel, go ahead.
I'm trying to understand this issue of this Skyrmion thing, because I understand Skyrmions as a static solution of some classical equation of motion, right? And it's static. So it has a group symmetry SO3 in the case of the usual Skyrmion. But here you're talking about transient phenomena, right? So you're talking about non-equilibrium physics, and you have a driven system. How is it that I can actually reconcile my ignorance on Skyrmions being a static solution and something that is transient phenomena on terahertz scales? And basically shake up spins and they will relax and there will be transient phenomena and all of that, whether calling that a Skyrmion. I would like to understand this. Yeah.
Right. Okay. So I think I kind of completely see the question. I should mention that the concept of the momentum space kind of Skyrmion is an extension to the definition of the conventional Skyrmion. In other words, there are some connections between the way spins behave in momentum space. So if you were to take all the kind of transient, like say frequency dependent behavior and compress all of it onto a lattice and say that for the case of discussion, let me just show this. So let's say these are the various frequencies, and these are, can imagine these to be the spin vectors. Now, for the sake of discussion, I could just kind of only consider these spin vectors and not worry about the fact that these are at different frequencies. Then you will see that this spin texture does map directly to a kind of static spin solution of a Skyrmion. That's really the extension of the concept that you're mentioning. Yeah. So that mapping can be shown to be rigorous. And it can also be shown, for example, on a lattice, that if you have a lattice in which you assign the spins, then if all the spins are aligned, then it's really a trivial phase. But if you have spins, say, at the four corners of the square, where two spins are aligned up and two spins are aligned down, that texture supports these edge waves. So we have been able to prove that rigorously as well. Daniel, I think you are muted.
So this is a texture in frequency space. It's not
Yes,
a configuration space.
exactly. Right. Yes.
Right, I don't want to keep you too long, so if there aren't any other questions, then again, I wanted to thank you for your time and your presentation and joining us today. So if that's it, thank you very much.
Thank you, everyone. Thank you for the wonderful questions, and thanks, PTech, for the invitation. Thanks, Jenny, for organizing. It's been a pleasure.
Yeah, and I can send you a recording if you'd like. We'll post it
Yeah.
on our YouTube channel, and I'll send you the link.
All right. Thank you so much.
Thank
Take
you
care.
so much. Bye.
Bye.